Good morning, everyone, and welcome to part 4 of the FoRRwD webinar series. My name is Mike Fitch with the Ohio LTAP Center here at ODOT, and we appreciate your participation. As we get started, please take a moment to locate the questions box in the GoToWebinar panel. During the presentation today, please use the questions box to send in any questions you might have. With that, we will go ahead and turn things over to Ray Brushart. Hello.
Hello, Mike. Thank you very much for being the host
Yes,
today.
you're welcome.
Hello, everybody. This is Ray Brushart with the Ohio LTAP Center, and congratulations. You've made it to the last session, part 4 of 4 of our FoRRwD webinar. So it stands for Focus on Reducing Rural Roadway Departures. And I guess we'll just sort of pick up where we left off last week. We were talking about clear zones. And we'll start on this slide here. This table you see is from the Ashtow Roadside Design Guide, which provides guidance for the width of the clear zone. And the values that you see in this table are based on a couple of studies that found that about 80% of vehicles stopped within 30 feet of the traveled way. So once a car went off to the right side of the road, they usually only went about 30 feet away from the roadway. So based on that, they just said, well, let's just make the clear zone requirement 30 feet. And the values were factored for speed, average daily traffic, and side slope, but are still considered to address about 80% of encroachments, or 80% of vehicles that go off the right side of the road. So the Ashtow Roadside Design Guide is your reference for this information. And you see a picture of the Roadside Design Guide there on the top right of the slide. And you can just Google this and you can find it. That's a good resource. And then we talked about what is traversable. And so we have this table here to talk about. So roadside slopes that are a 3-to-1 or flatter are considered traversable. So this means that in most cases, an errant vehicle can cross over these slopes without rolling over. That's pretty key. We don't want the car to roll over. Remember, the rollover crashes are one of our what we call our low-hanging fruit of crashes that we want to do our best to take care of, to lessen the number of these types of crashes with a low cost improvement. So flattening the slopes to 3-to-1 or flatter is what we're talking about here. And then slopes that are 4-to-1 or steeper are also considered recoverable. So recoverable means that the driver can actually start recovering control on the slope. And slopes that are steeper than 3-to-1 are considered critical, and depending on their height, a barrier may be appropriate. And so we talked about the pictures. The picture on the top right is from Florida, and the picture on the bottom is from Washington State. So it looks pretty scary there, doesn't it? So there looks like a place where they cut down a lot of lumber, doesn't it? So rollover crashes. We got some statistics here from the FoRRRwD system, the Fatal Accident Reporting System from FHWA or USDOT. And so why are adequate clear zones and traversable slopes important? Well, if we look at these statistics, we can see that rollover fatal crashes predominantly occur in rural areas with posted speeds of 50 miles per hour or greater, and almost half of those occur on curves. So we'll see a theme here with curves. For such a small percentage of the roadway miles, they are well overrepresented in crashes. Only about 5% of roadway miles are curve miles, but yet we see they're responsible for a big percentage of crashes here. So I showed you a video last week. Might as well, it's next. Might as well take a look at it again. So that was at full speed, and now let's take a look and slow it down, see what happens in this rollover. So that was filmed over in Germany. So anyway, I think that guy just got lucky. What do you guys think? Because I don't even see any protective equipment in that car. But as you can see, when they slowed it down, I think he just got lucky because it didn't really fall like square on top of the roof of the car. It always hit on the side. So unless there's rollover bars in that car, which I don't think there was, maybe there was. I don't know, but that's what happens in a rollover crash. It's not just when you're going 55 miles per hour, it doesn't just roll over on its side and that's it. So usually something like that happens with rolling over multiple times. So you can see how violent a rollover crash can be. Okay, so here's where we really left off last week. So here's a picture showing basically a before and after. And this is in Alabama. And actually, this is a scene of a crash where the actor Morgan Freeman had a rollover crash. So you can tell by looking at that what's before and after. So we have in the after, it looks like the slopes of the ditch were flattened, and the clear zone has been extended, and there is a paved shoulder. So in the after, you can see that that they made the slopes traversable and recoverable. But it definitely could create the before could definitely create a rollover crash. It's like 5 to 1. And then up in the table here on the left, that's a table from the Highway Safety Manual that shows the crash modification factor for flattening slopes. So crash reduction anywhere from 21% to 6% by flattening some slopes, depending on the before and after, whether you're 2 to 1 up to a 6 to 1 or 5 to 1 to 6 to 1 and so forth. And again, they have these playing cards up here in the top right that FHWA has printed up. You can order these playing cards, and they have a picture on one side of shows the countermeasure and the crash reduction, expected crash reduction factors on the back. So that's another countermeasure that we have, is flattening the slopes to prevent rollovers. And our next countermeasure that we have is working on the ends of culverts to make them traversable. So transverse culverts. So what we have a picture of there, it's a pretty large pipe. It's at least 36 inches, maybe more, but it says single pipes up to 36 inches. We can cut those to match the side slope. And so the car doesn't have to hit a strong fixed object, which is obviously not good. But the full-scale crash tests have shown that even at low speeds, vehicles can traverse openings up to 30 inches between pipes on side slopes up to 3-to-1. Single pipes up to the 36 inches can simply be cut to match the side slope. Grading beyond the pipe is also very important and should be made traversable. So the other case is these parallel culverts. Single pipes up to 24-inch can be cut to match the slope. Slope should be 6-to-1 or flatter. And if your pipe is greater than 24 inches, then the pipe runner with 24-inch openings can be used to make them traversable. So I think we've all seen situations where we have these pipes underneath driveways, and they're a fixed object to errant vehicles, and so we can do this treatment so the crashes won't be as severe, or they could just be property damage only crashes. Okay, so when we say an unobstructed area, when we talk about clear zones, let's talk about what is unobstructed. And so, although many other fixed object types are out there, let's focus on the two low-hanging fruits of trees and utility poles. So let's first talk about tree crashes. What can we do about those? So tree crashes result in 65% of rural fixed object fatalities. So trees are very unforgiving. And so we can see with the pie chart on the left that of the fixed object fatalities, trees make up the biggest percentage. So tree crashes. Tree fatality crashes predominantly occur in rural areas, but 1/3 occur in urban areas. So if we take a look at these statistics, on roadways that have a speed limit greater than or equal to 50 miles per hour, it's makes up 63% of rural roadway departure tree fatalities, and then 35 to 45, 31%. 50% of rural tree fatalities occur in curves, and 62% on collector and local roads. So let's, I think I have a video here. Tree crash test. So this is from Europe. So those are kilometers per hour. So 50 kilometers per hour, 70 kilometers per hour. And then you have 90 kilometers per hour. So pretty shocking what happens with the speeds of up to 55 to 60 miles per hour with a tree. So as you can see that the engine is all the way back, probably in the back seat of the car in those types of crashes. So that's not good, right? So that's the difference in the damage to cars and to the people at different speeds there. So the video is produced in Sweden, and like I said, the speeds are in metric. So 50 kilometers per hour is about 30 miles per hour. 70 kilometers per hour is around 43 miles per hour, and 90 kilometers per hour is around 55 miles per hour. So what you saw in that video is 12-inch diameter green utility poles held in place by a frame to simulate the support a tree has in the ground. This approach was taken to ensure the same support condition and were available for each crash test at different speeds. So that's what was going on in that test that they were conducting. Okay, so clear zone improvements with trees. So it's understood that removing a single tree may be much easier than clearing out a dense forest. Can an incremental increase in the clear zone be achieved? Are there any strategies to keep vehicles on the roadway? So we're looking at this picture. We've all seen situations like this. So here we are at a curve, and it's a rural wooded area, and you see that we have trees right here. Looks like about 10 feet off of the edge of pavement. And so what we have here at the table is from the NCHRP report for FoRRWD, accident mitigation guide for congested rural 2-lane highways. And so we start off with an incremental an increase in obstacle distance, an incremental distance of feet. So we start off with 3 feet. This is off the edge of the pavement, so 3 feet all the way up to 15 feet. And if you can remove those trees, then you get an incremental crash reduction further away from the edge of pavement. And so the chart looks at trees, and then also in the third column we got mailboxes, culverts, and signs, and then we have guardrail, and we have fences and gates. So I think we've all seen these type of things as we drive down a rural road. So you probably see mailboxes. Somebody built a fancy stone or brick mailbox real close to the edge of pavement, which is probably illegal, but they do it, and then without asking permission, I'm sure. But maybe somebody in class has had some experience dealing with a property owner who has done that. If you have, let us know how that went. But this chart does exist, and so this is, the research has been done to show, instead of mowing down a whole forest, maybe we can look at certain trees or fixed objects and see about maybe only remove ones that are closest or in areas where we know we have a higher percentage of crashes, like this one here in the curve. And so you can use this table in your meetings with property owners or from groups that they don't want to have. There's some groups that don't want to have any trees removed, and but this is a source to help you in your negotiations when you deal with them, to show them the how you can make the road safer. Okay, so then we have utility pole crashes, and what do we have as a resource here to help us figure out what we can do to make roads safer that have a history of utility pole crashes? So here in the NCH report 500 that addresses utility poles, again, that's this NCH RP report 500 has several different volumes, but volume 8 deals with utility pole crashes, a guide for reducing collisions involving utility poles. So it goes over some strategies, depending on how much money you have for this sort of thing. But one is place utilities underground if that's possible. Another one is to relocate utility poles further from the edge of the roadway. And another is to decrease the number of poles per mile, like the pole density per mile. And so in this picture here, can the number of poles per mile maybe be reduced, or can we space the utility, space them further from the edge line in this picture? Is that something that we can do? I know there's obviously a right-of-way line somewhere, but it looks like there is room to move them further away. This picture is in West Virginia, by the way. I see the comment box flashing. Mike, do we have some comments or questions?
No, I just sent a general message to everyone that if they have any questions, they can use the questions box.
All right. Okay, so again, you can download that Report 500 as a resource. And again, we have the, Mike, didn't you say we have the PDFs of this presentation, part 5 and 6 in the handout? So
yes, in the handout section of the GoToWebinar panel, yeah.
All right, so if we look into that Report 440, then we can find this nomograph, and we can see how the safety can be quantified as when we talk about utility pole removal and relocation. And it can also be applied to trees, luminaires, etc. And so if we open up NCHRP Report 440 and look at page 70, we'll find this nomograph, which approximates the frequency of vehicle crashes with utility poles. The nomograph predicts crash frequency as a function of average daily traffic, average pole offset, and the density of pole placement, which is the number of poles per mile. The nomograph can be used to estimate the effectiveness of proposed countermeasures, such as increasing the average pole offset and reducing the pole placement density. So as we take a look here, with these red arrows that pop up, we're going to use a base case of 10,000 vehicles per day as our ADT. And as you can see, that red arrow goes up to a pole density of 60 poles per mile. And then we go over to a pole offset of an average of 2 feet off the edge of pavement. So this results, as you can see the arrow coming down to this number here, of 2.0 utility pole crashes per year per mile. And this does not predict severity, but frequency. Now, if your strategy is to do a joint pole usage, and then the number of poles can be reduced to 20 poles per mile, but maintain the same offset. If we did that, then we could drop the expected crashes per year per mile down to 1.2. So you can play around with the variables, or if you can also move the poles back to 10 feet from the edge of pavement, then the frequency could be brought down to 0.4 crashes per year per mile. And the same prediction model could be used for street trees to predict the effect of offset and density on various average daily traffic facilities. So we're also going to look at other objects, but there'll be breakaway objects when we get to module 6. Utility poles, they have different designs of utility poles now. They can be energy absorbing or they can be collapsing, but they're not widely used at this time. They also have something called a frangible base available in the design of utility poles. So, there is some new technology involving utility poles. So I guess we just need to start using that technology so we can start lowering the number of these crashes. So there's with those 2 clicks I just did, you can see where we got it down to 1.2 and 0.4 with different variables. Okay, so that's what we have on trees and utility poles. And now let's talk about the use of object markers. So if we cannot provide a clear zone free of obstacles, then we need to look into the use of object markers. And so if we take a look at some of these pictures, we see utility poles with an object marker on it here at the top left, and the trees in the middle here, which is in Hawaii, by the way. They have a solid yellow object marker to delineate them. So we have some object markers here. We also see some rumbles, the button type of rumbles that they use in Hawaii, because they don't really have a lot of snow plows in Hawaii, do they? So they can use those types of rumbles. In the photo on the right, the object marker is always placed at the edge of the hazard, since more than one exists here. So we have hazards on both sides of the road there. So to identify the first harmful hazard, if it can be marked with on the edge with the object marker at the edge of the hazard. In this case, the severe drop off is marked on the left, and in both sides of the culvert have object markers. So object markers are very important, especially in cases where we can't do anything else. And it's important that everybody use object markers wherever there is a need for them. And if you need to find out more information on object markers, you can find a lot of information in the Ohio Manual of Uniform Traffic Control Devices. So let's check that out. If I go to the Ohio LTAP website and click on resources, and then I click on the Ohio Manual of Uniform Traffic Control Devices, and then I click on Chapter 2 of the manual, and I go to Section 2C, 0.64, page 155. Can you see this on the screen, Mike? Then
Yes, yeah.
Then we have the all the information about object markers. So we have different object markers for different reasons. And so you can read up, there's different colors. The red would be for the end of a roadway. So yellow is warning, but then we have different shapes and different things like that to read up on. So, the standard of the alternating black and retroreflective yellow stripes is the OM3-L. The L stands for left. That's the left side of the roadway. R stands for right. So the stripes slant downward to the direction where that traffic is to pass it by. So it passes by on the left of this sign and right of that sign. And so there's standards, options, and things like that to look at. So if you need to find more information on object markers, Chapter 2C of the OMUTCD. Let's get back to part 5 here. Okay. So yeah, anytime you have a head wall of a culvert, a narrow shoulder and a steep slope, a drop off, or trees that you can't do anything about, or utility poles that can't have anything to do, we can't do anything about, then object markers need to be placed on them. And don't forget, maybe you should have some white edge lines as well to keep people on the side of the road. So here are some more resources about some of these countermeasures from the Federal Highway Administration. So I want to make sure everybody had a link so they can read up on different countermeasures from the Safety Edge or the Roadside Design Guide or anything to do with horizontal curves. So here's the from FHWA safety program, the low cost treatments for horizontal curve safety, and they go over a lot of different things in that book. Very good resource. Okay, so let's go over our session 5 learning outcomes review. So let's where do you prefer? We'll have you answer in the question box, right, Mike?
Yes, the questions box is open.
Okay, so what do we have here? It says identify countermeasures that can reduce the potential for a crash if a vehicle leaves the roadway. So what are the countermeasures that can reduce the potential for a roadway departure crash?
Okay, David just typed in, is there a program in Ohio to remove trees near roads? I see a lot of removal along Route 78 east of Nelsonville.
Well, I would say the program begins with contacting that district's safety engineer, somebody on the district safety review team, and you can begin those discussions with them, and they can bring up some crash data there, and maybe they already have a file started on particular trees and stuff. So that's maybe not a program, but we have we have people to talk to, and you would begin that discussion with them. So that would
Thanks,
be
Ray.
Nelsonville is in District 10, which is in Marietta.
Thanks, Ray. And in response to the question on the screen, Michael says safety edge, object markers, make slopes traversable. Curtis says clear zone, recoverable slopes, remove obstacles like trees, markers, guardrails. Tanvir says pavement safety edge, wide shoulders with traversable clear zone. Matt says remove obstructions in the clear zone. Kevin says slope reductions, conduit end treatments. Sarah says tree removal, shoulder restoration, improving slopes, and object markers.
All
And
right.
David says clear areas and flatter slopes.
Okay, very good. So providing shoulders along the roadway, remember we talked about that. They definitely have a safety benefit. Then we have the safety edge. Another treatment was a center buffer area to cut down on the head-ons and opposite side direction side swipe. Then we got into the clear zone, talking about it with traversable slopes or recoverable slopes. Okay, so very good, people. Let's go into another question here. Multiple choice. Let's see if we get some right answers here. Define the clear zone. So which of these are true regarding the clear zone? A, it's an acne medicine. Huh? What? Yeah, there actually was an acting medicine. Have you seen that commercial? It's been a long time. Okay, so B is it's the furthest distance a vehicle will go when it runs off the road. C, it is the unobstructed traversable area provided beyond the edge of the through traveled way for the recovery of errant vehicles. Or D, the clear zone does not extend outside of the right of way. So what do we think here? A, B, C, or D?
So Ray, multiple people are typing in answer C.
All right. Well, I think they nailed it, don't you? So C is definitely the correct answer. In this definition, you would find that exact definition in the Ashtow Roadside Design Guide. So it turns out A was true also. Did you see that? There it is, clear zone. Okay. Okay, let's get into our knowledge post-test. Okay, I want some good interaction here. You're getting a certificate for this, for gosh sakes. So what improvements were made to reduce the potential for a crash if a driver leaves the roadway? So we're looking at the before picture and the after picture, and let me know what countermeasures that you see in the after picture. Let's see if anybody gets them
Okay,
all right.
so Brent typed in increased shoulder width. Michael says trees and grass cut, shoulders widened, double median stripe. Kevin says center buffer, paved shoulders, and tree clearing. Tanvir says added shoulders, safety edge, centerline buffer. Sarah says paved shoulder, increased lane separation, and tree clearing. Matt says transverse yellow lines, and Barbara says widened shoulder, painted median.
All right, very good. Let's see here. Do I have at this location paved shoulders were added? You can see in the picture there the nice paved shoulder. Looks like about a 2-foot shoulder paved. And there appears to be a bit of an edge drop off that could be mitigated if the safety edge was used. So I don't know if they used a safety edge. Maybe they should have used a safety edge. There's also a centerline buffer area. Someone mentioned that, Mike?
Yes.
Okay. They get a gold star. What else do we have? The clear zone looks good both before and after, but a tree appears to have been removed from the inside of the curve too. Yeah, so this big tree here appears to have been removed. So they've studied this big tree over here, and they left it because, well, it's a nice big tree, but it's also pretty far off the edge of the pavement. It's still in that straight section of roadway before the curve. So maybe that's why it got lucky and was allowed to stay. Okay, so that's very good discussion on for our module 5. Very good. Is there any other questions or comments or concerns from anybody, Mike, on our
Ray,
module 5?
Michael typed in, he says, by the way, I think the 55 mile per hour speed limit sign right in front of the cautionary sign is not a good thing.
Yeah, it kind of makes you wonder why they put a speed limit sign right there. So usually you find a speed limit sign just after like a major intersection, or if you're on a freeway, you'll see them, right after an interchange or something like that. So it's a good point there. We don't want to create driver confusion. And it's just too close. I mean, you're going 55, it's hard to, things can be a blur there. So I agree. Okay. Well, if no more questions or something to talk about, we can move on to our module 6. Let's see if I can find it. Here it is. By the way, when we're done with module 6, I'm going to talk about an actual ODOT project that involved several countermeasures all in one project. Countermeasures that we've discussed in all 4 parts. So module 6 is titled Minimize the Severity of a Crash. So basically we've done all we can do. We've tried to keep the vehicles on the road, which was our first strategy. And then the second strategy was to provide a recoverable area off the side of the road, or maybe even make it so they can get back on the road if they drifted off. And then in our third part, we talk about that a crash actually happens and what we can do to minimize the severity of that crash. So the main learning outcome of this session is to develop an understanding of countermeasures to reduce the severity of crashes. So on the left here, we see a breakaway signpost, the hardware for it. And on the right, we see a picture provided to us by NCHRP, shows the testing of a type of guardrail there. Okay, so the learning outcomes for session 6 is to, first of all, identify crash-worthy sign support systems. And then we'll talk about identifying the essential elements of a barrier system. And then we, hopefully at the end, you'll be able to recognize common installation issues for roadside hardware. So here's our knowledge pre-test. So if we take a look at this picture here, can we identify what might affect the performance of the barriers shown? Anybody see anything? You might want to write it into the question box if you have an answer there.
Kevin says curb.
And what's that curb basically going to do in this case?
Barbara says prior damage. Michael says guardrail end treatment.
So if a car comes through there, what's it going to do? What's it going to end up doing?
Matt says guardrail not connected to parapet wall. Curtis says need to attach to barrier, eliminate curb. Sarah says not connected to wall, bridge, rail. Khalil says discontinuity. David says guardrail guides car to hit abutment.
Yes, gosh, isn't
Stephen
that
says
terrible?
curb could cause vehicle vaulting.
Yeah, it kind of makes you wonder why the curb's there. Obviously, something was going on there that they arrived at that decision. Okay, so good answers, but let's see. So this, if you're wondering where that is, it's from the Tacoma, Washington, State Route 7, and it's from FHWA. So the old guardrail, so it is old guardrail. Says no block and 12-foot 6-inch post spacing may not contain the vehicle. Curb is in front of the guardrail, which might cause the vehicle to lift, hitting the barrier higher than normal. The guardrail is not connected to the bridge end. The guardrail might lead the vehicle into the end of the rigid bridge rail. And the bridge rail itself, says curb and parapet, might cause some instability in a vehicle. So basically, it's just not good all the way around here. So stay away from that stretch of roadway, please. Okay, so here's our, if we go back to the beginning of our class, our roadway departure objectives, of course, number 1 was to keep vehicles on the road. Our second objective, reduce the potential for crashes, and third, minimizes severity. So that's what we're going to be talking about here. One of our resources here that you can view and download is called MASH, which stands for Manual for Assessing Safety Hardware. So there's the 2016 version, which was the second edition. So in this first part, we're going to talk about breakaway devices and barriers. So first thing is breakaway supports. What do they do for us? So reducing severity by providing breakaway hardware. So that's, we're talking about sign supports, luminaire supports, utility poles. And so if we recall from session 2 of the MUTCD requirements for curve signing, similarly, the MUTCD requires sign supports to be crash-worthy because they are fixed objects with the potential to harm the occupants of the vehicles. Crash-worthiness is determined by MASH standards, and each vendor or agency is responsible for testing and assurance. Luminaire supports and utility poles come under Ashtow guidance. So there's a booklet called Structural Supports for Highway Signs, Luminaires, and Traffic Signals, which you can look up. Okay, so here's some different options for crash-worthy installations. So there's 3 methods which are allowed for crash-worthiness. So in the first picture, we see a bending or yielding where the material fails and either bends downward or yields due to the force of the impact. Slow impacts are generally not sufficient to bend fully or yield completely, but reduces the severity of the crash. LTAP splices are generally not practical as a standard, but some states have approved a LTAP splice which satisfies the criteria of yielding at impact. The height and length of splice and front and back members are critical for performance. No more than 3 posts in a 7-foot circle of 3 pounds of the or less and must be breakaway. Direct, driven, or field splices only 2 foot in a 7-foot span. Direct variable is acceptable given proper depth, soil type, and structural steel properties. Then we have the slip base in the middle for lightweight structural steel, number 3 or less, shown, and then our medium weight, which is 3 to 6 pounds per foot. Let me see what else we have here. There's something else. No. And then we have or I-beam designs, which are not shown, but those are even stronger, 4 foot to 30 pounds per foot. And in the right is a breakaway designs, of which there are many, generally a small coupling device, a neck down bolt, or something like that. So there is a link at the bottom of this slide, which is from the FHWA safety website, roadway departure, and then gets into road hardware and sign supports. So that's where you would find a lot of information on these different types of crash-worthy installations. And there are some sign support design considerations. So large signs usually have multiple supports. And then we have on the picture here on the left a T intersection. And the slip base is not oriented for traffic on the main roadway. So it's designed for somebody running straight through the intersection in that case. So we consider the direction of impact, whether it be unidirectional or omnidirectional. So if a support is likely to be hit from different directions, an omnidirectional design may be appropriate. So that was something to consider. And then we have other sign support design considerations. We talk about slip bases. They have torque limits. As you can see in that bottom picture there, torque limits on this big bolt here on the left. And then they have something called a keeper plate there. Slip bases have torque limits. If they're too tight, they may not slip in an impact. Once the base breaks or releases, the stub should stick up more than 4 inches, or not stick up more than 4 inches, or it could snag a vehicle. So we can see here in the right about this 4-inch max of the stub of a sign. So that's something that we consider when we install these types of signs. Then we have some more pictures here. Signs with multiple supports. If supports are closer than 7 feet, they act together. So large signs usually have multiple supports. If the posts of a multiple support structure are within 7 feet, then there's a likelihood that more than one post will be hit in the same event. If posts are within 7 feet of each other, they are only considered crash worthy if they have been crash tested together. Otherwise, the post may act more like a barrier and won't give when a vehicle strikes them. So on the left, we have a sign with multiple supports within 7 feet. Some smaller supports may have been tested with the vehicle hitting 2 or more. In the middle, we see this appears to be 2 large supports that are within 7 feet. And on the right, we can see where a vehicle was able to miss both supports. So we can see in this picture, we had the proper width and the errant vehicle was able to drive between them without hitting them. Isn't that wild? So there's a good reason why we do that. And in this case, we see large signs of multiple supports also need to have a breakaway mechanism at the base and a hinge just beneath the sign panel. The hinge is located at least 7 feet above ground level so that a vehicle can travel underneath the sign panel. Keep in mind that this clearance height is measured from the ground level at the post and is different from the MUTCD requirement, where you need at least 5 feet from the top of pavement to the bottom of the sign for legibility. So that's some more design considerations. And there's an example of what we expect to happen in that case. You see the breakaway at the bottom and the hinge at 7 feet above the ground level. And then the car is able to pass through. So there's why we need the 7 feet of clearance in that hinge at the top. And down here at the base, we don't want that to be more than 4 inches because it would have snagged this vehicle. So that would have made it more like hitting a fixed object, which we're trying to make sure that we don't have that situation. So that's sign supports, and I gave you some a link for more information for the sign supports. Okay, so let's move on to our barrier systems. You've probably seen barrier systems placed on our divided freeways. I-270 around Columbus has a lot of spots in there that have barrier systems installed. So barriers are fixed objects that can result in injuries when hit. So the most common barrier systems are cable barriers, W-beam guardrail. I was talking about cable barriers when I was talking about the ones on 270. between the opposite directions of lanes in the median. And concrete barriers. So, but the focus for this presentation will be the W-beam guardrail. So we'll first talk about the W-beam guardrail. Barriers are often a last resort, and we'll look at the different parts of barriers, requirements for use and testing, and common problems with installations or in-service barriers and maintenance concerns. If objects or harmful effects cannot otherwise be mitigated by removal, relocating, replaced, made crash worthy, then a barrier may be the last resort. Barriers will sometimes increase crashes, but the increase is usually the minor variety type or incidental contacts. So as you can see in the pie chart, that barriers are fixed objects. So we do have a lot of crash data involving barriers, and they are responsible for over 300 fatalities per year nationwide. So let's take a look at the latest design of these so we can lower that number. So barriers are systems, and the components need to be compatible and continuous. So this is a figure from the Roadside Design Guide, which shows the different components. And this photo shows a location where the guardrail elements are not continuous and is exposed. So let me see here. So here's an example of it's not continuous. So we don't want that type anymore. So, but this type here shows our different components from from left to right. You got the downstream terminal or in treatment, and then we have a standard section. This is the length of need that we'll talk about. Standard section followed by a transition, and then like a bridge rail here that we attach to. Again, we have a length of need on this side to protect from whatever's down, whatever this bridge is traversing. And then another upstream terminal or in treatment. So it's important to ensure tension continuity throughout the system. Okay, so MASH, they're the ones responsible for testing these barriers. And again, there's the resource that you can download. MASH, again, stands for Manual for Assessing Safety Hardware. So the other requirement of a barrier is proper in-service demonstration of acceptability or performance for its intended purposes. And that's stated in the Roadway Design Guide section 5. And so we have up here at the top, we have these two pickup trucks. And so we have a new test vehicle, which is a quad cab pickup truck of 5,000 pounds. So the one on the right here, that's the new vehicle to test, has a higher center of gravity and more closely represents large SUVs. So that's good to know that these are being tested, right? Because you can't drive down the road without seeing a gazillion large pickup trucks and large SUVs. So it's good to know that the barriers are designed to help them in a crash. So there's been some test level changes. So the primary variables that are in the crash test criteria, they look at vehicle mass. So most testing involves the small cars and the pickup trucks. And the speed varies by test level. Also, the angle of impact is tested. There's different angles of impact. So most testing is where the vehicle impacts the barrier at a 25-degree angle. And so we look at this as an example here, TL3 in the middle here at let's see, at 100 kilometers per hour is the basic test level for most high-speed roadways. So, 100 kilometers per hour is going to be more than 60 miles per hour. TL-1 and TL-2 are the same conditions, but run at lower speeds. So remember, in all these tests, the pickup truck impacts the barrier at 25 degrees, and under using NCHRP report 350, the 1,800-pound car impacts the barrier at 20 degrees. This was changed to 25 degrees in the latest version of MASH. And a TL3 at 62 miles per hour here in this table versus a 75 mile per hour speed limit. They did a test on that. Impact speeds were studied as part of NCH report 665. The 62 mile per hour represents about the 85th percentile of speeds on the divided highways. The 25-degree angle also represents the 85th percentile. When combined, there are less than 5% of crashes where the speed and angle exceed the test conditions. So that's how they arrived at why they study at those angles. Let me see something here. Okay, I want to check the time. We'll make sure I'm not going over here. Okay, so in the new MASH, it includes a new barrier for slopes, fixed objects, medium barrier, and upgrading existing hardware. Okay, so there's different considerations for different barriers. There's they look at height. What is the height that's needed? What end treatments are needed from terminals, anchors, and transitions? Let's see, the height requirements, the tests are done with the top of rail at 25.5 inches from the ground. That was not successful. So the roadside design guide recommends raising the rail that is at 26.5 inches as part of 3R projects. The primary barrier considerations include the following. End treatments naturally include some of the placement considerations. Let me see. And of course, length of need. So let's take a look here at the guardrail height. Here's a guardrail height of 31 inches. And this system has been adopted in most states. And so let me see here. Let's take a look here. Let me start that over again. Let's take a look at a test with a pickup truck hitting the barrier at 25 degrees. So this is what happens at that angle. I like that. Let's see it again. For those who've never seen a crash into a guardrail before. So we're not talking about a simple side swipe that you might have in your head. We're talking about a situation that, you're coming in there at high speed at a 25-degree angle. So a little background on that. In the early 2000s, the Midwest Roadside Safety Facility conducted a study to develop a better performing roadside barrier. That research indicated that the performance of the G4 1S strong steel post guardrail improved when the splices were moved to mid-span. Increase in the blockout depth also improved crash test performance, as did raising the height of the rail from 27.75 inches to 31 inches, which reduced the embedment of the post. The MGS represents the combination of these factors. the MGS has also been crash tested with 8-inch blockouts, and the Texas DOT is currently, well, they've been doing it since 2012. They prepared to submit a request for eligibility. So that these studies have been going on, all the time, but a little bit of background from the early 2000s. Other systems were subsequently developed that also have a 31-inch mounting height. So you might have a question of when do you need to raise the guardrail when an overlay has reduced the height. So if you're overlaying pavement, like say you have a 2-inch overlay project, resurfacing project, so the Ashtow Roadside Design Guide states that guardrail that is at least 26.5 inches high after an overlay may remain in place. And it says, whereas new installations of strong post W-beam guardrails should be installed according to this guidance, and it's recognized that many transportation agencies have installed miles of barrier at 27 inches high based on previous guidance. This has resulted in barrier systems being installed at a height lower than the currently recommended heights found under the current controlled crash test conditions. Many of these existing systems have and should continue to have acceptable real-world high impact performance. It is not cost-effective or practical to raise all existing guardrail to the current criteria on a highway agency's entire roadway system. However, guardrails should be upgraded as part of a reconstruction or new highway construction project. So that is what the Ashtow Roadway Design Guide says in response to that question. So let's talk about guardrail anchors. And so we'll have another video for you. So an anchor is needed on each end of a guardrail to develop the strength of the system. The anchorage is usually part of a terminal or transition and may be all that is needed on the trailing end of one-way roads. So let's take a look at a video showing the function of the anchor with a downstream hit. The anchor includes the cable, connections to the guardrail, post, and strut. Let's take a look here. So you can see how it pulling on the anchor there and the impact. Let's see it again. So it says the photos from Kentucky show a location where the cable anchor may not have been connected at the time of impact and the vehicle was able to pass through the system. Let's see, that's a different. We're talking about this picture here. So this picture from Kentucky shows where the cable anchor may not have been connected at the time of impact. So the vehicle was able to pass through the system. And you can take a look at the skid marks here. So you can see that the angle of this impact was basically the same as that pickup truck in the first video showing, that it came in at that angle. So basically it's not supposed to break away like that. So it did not perform correctly. So that's why they're saying that it may not have been connected at the time of impact. Okay, so let's take a look at these guardrail terminals. So the terminals now need to meet all MASH requirements. So there are older designs that have been used that differ in regards to a flared section versus a tangential section. The terminal is flared away from the road at least 4 feet, and the terminal is tangent or parallel to the road. And then you have gating or non-gating, which will let a vehicle travel through it rather than being redirected. And then there's energy absorbing or non-energy absorbing, where the terminal end is designed to absorb energy from a head-on strike rather than an end that doesn't absorb energy. Each of the terminals includes an anchor for developing the strength of the system. And so the photos show different current MASH terminals. So in the left, we have something called the MSKT, and that's pictured from the state of Washington. The middle top photo is called Soft Stop, which is shown from Texas. Then we have the middle top photo, which is Max Tension Design from Massachusetts. And the bottom right photo is where we have the end is buried into the back slope, and that's from it just says from FHWA somewhere. So I don't know if I've ever seen that before, but in that situation, that's what they decided to do. Terminal grading sometimes is needed. So for a terminal to work properly, the grading around the end is critical. So there's 3 areas of grading: the advance area that you see over here, where the vehicle is traveling before impact. A flat area helps reduce instability. And then we have the adjacent area, which is around post number 1. The flat area reduces instability and provides soil embedment for the anchor. And then over here is the run out area. A recoverable slope is desired. So here's a picture. If we take a look at this picture, is the proper grading in place? And if you can see the soil plates in space under the strut, then the grading is not correct. In this case, the anchor may not be able to develop the strength of the system. Because the posts are too high out of the ground, the vehicle may not break off the post or may snag on the stubs. This installation may not work for either purpose for the end treatment. So that is, they got some flaws in this system. Looks like it's not even done building it yet. Then we have our guardrail transitions. They're needed when connecting to a stiffed system. May also be used to reduce the deflection distance. So guardrail transitions, like I said, they're needed when connected to a stiffed system. So here's some examples of MASH transitions. This is a MASH TL-2 transition up here at the top. The concrete parapet is a 36-inch single slope bridge rail. And there are several transitions that have been tested for 31-inch guardrails. In a TL-3 rail transition, so there was a FHWA eligibility letter, and it's discussed in NCHRP 350 and in MASH. Okay, so the bottom picture is from Wisconsin. That's the TL3. So the TL3's got these nested rail elements, and it has additional posts are added at half the spacing. So they obviously have different designs for different situations. And then we talk about soil support. And Ashtow recommends placement of the barrier at least 2 feet from the hinge point of the slope if the slope is steeper than 1 to 3. So the hinge point, if you see in this picture here where the yellow line intersects these red lines, you can take a look here. It looks like more flat and slope begins. So that's the hinge point. If the rail is placed at the hinge point, the system may not work effectively because without adequate soil support, a strong post system will deflect too much and a vehicle could go over the top of the rail. You can use longer posts to counteract the lack of full soil support. Let's see what else here. So the MGS was tested with 6-foot long posts at the hinge point of a 2-to-1 slope and can be used with steel or wood posts and 8-inch or 12-inch or no blocks. And the MGS was tested with 8-foot long steel posts 12 inches behind the hinge point with a 2-to-1 slope and can be used with 8-inch or 12-inch blocks. So it was going over, Ashtow was going over the different positions of the post before or after the hinge point and what's needed in those locations. Because every roadway is different, right? Then we have our length of barrier. So what is the purpose of this particular barrier we see in this picture? And do you think that the barrier is long enough? So in this photo, the barrier is obviously here because we see a very steep slope or a cliff. And the last 12.5 feet of this rail will not redirect a vehicle. So a vehicle that hits on this end might still get into the steep slope. So I guess the answer would be no, it's not long enough. Maybe it should have been started, prior to that. So there is an Ashtow approach for developing the length of need. And so if we take a look at this picture here, in order to hit a roadside feature, a driver has to run off the road at some distance ahead of the feature and at some particular angle. All we really know about the angle is that it decreases at higher speeds. So the Ashtow design procedure does not specify any encroachment angle. Instead, it uses what's called a run out distance and the lateral offset to the back side of the hazard to determine an appropriate barrier design. The assumption is that a driver will try to bring the vehicle under control and try to return to the roadway. If he or she is behind a barrier, then the only choice is to bring the vehicle to a stop. So the whole process hinges on the run-out length, defined as the stopping distance off the pavement. So here's the edge of traveled way, and they've come up with this run-out length, L sub R. And the point is they don't know, how the car is going to end up. However, it goes off the road and at some point would hit the obstacle. So the length of need is based upon these assumptions, so that whichever speed and angle, we'll try to make sure that it does not hit that obstacle, right? So run out length is defined as a stopping distance off the traveled way. So here's some suggested run out lengths. Let me see what time it is. I feel like I'm running out of time, Mike. I kind of am. So this is from the Ashtow Roadside Design Guide, and for determining run out lengths. It's on page 5-50. So as you can see, the run out length is a function of the design speed and traffic volume. And you'll note that the distances range from 470 feet for high speed, high volume facilities to 70 feet for design speeds of 30 miles per hour and traffic volumes under 1,000 vehicles per day. Some states use lesser distances based on different accident studies. So these values are different. They're lower from previous versions of the roadside design guide and are based on a study called the Cooper study. And the study that documents the basis for the lower runout lengths is in the Transportation Research Record 1984, and it's called Guardrail Runout Lengths Revisited. And then we have another calculation method called similar triangles. Let's take a look here. So if you have in this instance, a design speed of 60 miles per hour and your average annual daily traffic of 8,000, this line represents the edge of the traveled way, and the back of the obstacle is 30 feet from the edge of the traveled way. So we use the similar triangle method. So we're using proportions. It says the field check method would be to pace or measure the length of run out from the obstacle and look back to the obstacle. If the guardrail is intersecting the sight line, it is probably long enough. So in the top picture here, you have the end of barrier need. So they sometimes use this method. So there's the guardrail that you would want the barrier to be at least that long, and then begin the transition and end treatment. So in that case, the length of runoff is 250 feet with those particular dimensions and variables. And then here, if the barrier design on a horizontal curve can be done graphically, it can also be done for tangent sections. We first define the hazard, next measure upstream a distance L sub R from the hazard along the edge of traveled way, then define an envelope of protection from the end of the runout length to the back of the upstream face of the hazard. Now various designs using different barrier offsets and flare rates can be drawn to intercept the envelope. So here's the horizontal curve. Example of barrier designed for fixed objects on a horizontal curve. There's the offset from the edge of pavement at that critical part of the curve, and the runout length. Let's see here. So if the obstacle is on the outside of a horizontal curve, the length of need is defined by a tangent from the obstacle to the edge of traveled way, and this is best determined graphically. And we can see the runout path should actually extend to the river rather than stop at the bridge end. So we have to use some caution here. It says, since guardrail terminals pose a greater risk than a standard run, and since many roadway departures happen on curves, it may be more desirable to extend the guardrail around the curve in some cases. So even though your object is here, we want to continue the barrier all the way through the curve. So you don't end it there. So may want to extend the end all the way out to the end of the curve. Here's our terminal section. So let's talk about this terminal section here. Is this the best terminal for this location? Could they have done anything differently to make it safer? So I'm running out of time, so I'm just going to go right to it. So it says a BIB may have been more appropriate here. Either way, the barrier appears to be too short to keep a vehicle from getting to the steep slope. Looks like somebody could just go right through there. So maybe the buried in to the slope treatment that we saw a picture of may be better here. Again, there's a resource on the FHWA safety website on road terminals. How about here? Was this the best place to end this guardrail? Doesn't look like it, does it? That looks pretty scary. So the right photo shows an inadequate length of need. A vehicle could easily pass behind the rail and hit the trees or the slope. It also didn't have the advanced or adjacent grading. And in the left photo, it shows that the barrier, if the barrier had been a little longer, a flatter slope would have been encountered. So this is like a cliff here. If we would have extended it back, then it could have been a flatter area is what it's saying. So there are some more resources here to do more research, to provide more information. Again, the FHWA Office of Safety website, they have a medium barrier information and roadside design information as well. Okay, so let's get to our, then we'll run out of time. Let's get to the our learning outcomes review. So the question is, which of the following is a type of crash-worthy sign support system? A, B, C, and D.
All right, and the questions box is open.
I think we're running out of time, so I'll just let you know that says the answers are A, C, and D. And apparently they have not developed a floating sign system yet. So maybe they had those in the Jetsons cartoon, but they haven't designed those yet here. So base bending, slip base, and breakaway. How about can you identify the essential elements of a barrier system? What are the components of a barrier system? All right, let's get to it. So we have the standard sections, the terminals, and the transitions. And here's another question. Which of these are common installation issues that could affect the performance of a guardrail?
Ray,
So,
Kevin typed in ABC.
ABC is correct. Kevin, you're the big winner today. So length, placement near slopes, inadequate terminal grading. So the color of the rail may be an issue in some areas like national parks, but it would not affect the performance. Okay, the knowledge post test. Remember this picture at the beginning? What improvements do you think will reduce the severity of crashes at this scary location? Let's see. Here's what they actually did in the picture to the right. So everything still looks the same, but what they did was they updated the guardrail. The guardrail was installed over the curb, and a transition was installed between the approach guardrail and bridge, and the bridge rail was retrofitted. So those were the improvements that they made. So apparently they got rid of the situations that might cause major instability at crash or launch a car too high at the guardrail impact. As you can see, everything is there so that it does not direct you into that bridge abutment that was retrofitted. Okay, so that was it for part 6. I didn't get to my ODOT project, but it involved a project over near Gahanna, where they installed several of these countermeasures. I brought that up here. Is it here? No, it was here. So that's not it. 6-1, was it this one? Yeah, this was it. So there's an area, Dirk Gross put this together for me. He's in District 6, but it was an area in northeast Franklin County, a 2-lane, 55-mile-per-hour road. There was 3 curves, and all 3 of those curves had crash histories, including a fatal in one of the curves, but the fatal involved a vehicle that lost a wheel. So that's bad news, right? But they installed basically better signage. They use micro surfacing as a high friction surface treatment. And, they did some before and after curve treatments with better signage. They actually had the wrong speed on one of the that we talked about, the advisory speed through a curve. They restudied it, put in a lower advisory speed sign. They updated the chevrons with post-mounted retroreflectivity as well, and they did observe in the end they lowered the number of crashes. And so he was just going over like before and after, but they did show really good crash reduction because they're all low cost treatments, like we said. So that was the whole point of this webinar series, using low cost systemic treatments, and different objectives for each one. Keeping vehicles on the road, or making a recoverable space so they can get back on the road, and thirdly, reducing the severity of crashes. So we're hoping that these treatments have been around for a while now, so we're hoping that we'll see even more use of all of these treatments, and not just at ODOT, but all local governments, from the county engineers in Ohio to township trustees. And again, at LTAP, we're buying the signs for townships with our township sign grant program. So that's one of the countermeasures. So we're helping out that way. Cities and villages as well, if they have situations like this. So I hope that everybody liked this 4-part webinar, and we were all able to get something out of it. Do we have anything else, Mike?
No, I think we're good. So thanks, Ray, and thanks everybody for your participation today.
All right, thank you, everybody, and I'll get cracking on those certificates, okay? So thanks again. If you ever have any questions about any of this, feel free to give me a call at the Ohio LTAP Center. So goodbye, everybody.